All right, hey everyone. So we're going to look into more detail about the random forest classification. At this point, you should have already looked through the slide deck on random forest classification to have a little bit better understanding of what we're going to be kind of walking through. And then, so yeah, at the end of that slide deck, we did this example about predicting wins or losses based on um, how LeBron James has performed in his career in the playoffs. So let's look through our data set briefly. So I found this data set online where every row is a game of LeBron James's playoff career. So starting in 2006 when he played for the Cleveland Cavaliers, that is an NBA team. If anyone didn't know, LeBron James is an NBA player. Um, and it has all these information how he performed in that game. So when I pulled this data a little while ago, there he played in 240 NBA playoff games. The most recent one on this data set was this one right here, 818, when he played for the Los Angeles Lakers against Portland Trailblazers. Obviously, he has played in more games since then, but this is what data set we'll be working with. So let's get to it. So in this kind of section right here, I just uploaded our data set to a Jupyter notebook, renamed some of the columns so they made a little bit more sense, and then dropped some of the columns that I didn't think we need. And here we have our data set. So one thing with random forest classification, all of our input variables are going to have to be numbers. So we're going to try and predict this wins and loss column. And we're going to try and use variables that we determine from the rest of this data set. So in order for them to be numbers, I indexed home and away as 1 and 0. Home is 1, away is 0. And then for series, if you're not familiar with the NBA playoffs, there are 4 series a team has to play in order to be declared the champion. So you start in the first round. If you win, you advance to the second round, then to the conference finals, and finally to the finals. So that's going to be this column right here, series. And yeah, I think the rest of them are somewhat self-explanatory. So let's move on. I thought it'd be interesting if we looked at variables that we knew before the game occurs. So we don't want to base our model on stats that LeBron James puts up during the current game. We want to base our model on variables we know before the game actually happens. So we're declaring our X and Y variables. Our Y is what we're trying to predict, wins, loss. And our X's were the variables we're going to use in our model to predict that. So game per playoff run. Like I said, the playoffs consist of 4 series. Each series is best of 7. So a potential team could play 28 games in order to win the championship. So game per playoff run would be in this column right here. Game number, each series is a best of 7. So 1, 2, 3, 4, 5, 6. They won that series, advanced to the next series. Plus or minus is going to be the prediction of the game from Vegas odd makers. So like their team was predicted to win by 11. Home away, we already talked about that. And then series number, we already talked about that as well. Yeah, so like I said, all of these input variables or X variables can be determined before the game actually happens. So that's interesting because we can now use this model, if it is done well, to make predictions about future games, knowing information we know before the game even starts. So if you're going to be building models in Python, a lot of times you'll use this train test split. Basically, this splits our data set into training and testing data. So training data is what we'll be training our model with to build our decision trees, and then the testing data is what we're using to test our model with against data points from our data set that it hasn't seen before. So this randomly splits our data set into 2 two sub data sets. So my numbers and the rest of this slide are going to be a little different than the PowerPoint because I ran this right before I started recording, and it switched. It didn't choose the exact same training and testing data. So if you're following along in the slides, the values will be a little different, but all the concepts are still the same. So this will become important later, but basically I just pulled this win-loss column into its own data frame. All right, so let's look at our model. Let's see what we're going with here. So model is random forest classifier. N estimators is 100, is how many decision trees our model is going to make using our Gini index and using our bootstrap technique. The max depth basically means that each decision tree will continue to split based on different variables until every leaf or final node in that decision tree is pure. So they're all saying the same classification. So this is from our slide deck. So our model is going to create 100 of these decision trees. Right now we have 9 of them. And it's going to keep making these splits until every n node right here is going to all be the same classification. So in our case, they're either all going to be win or all going to be lost. It's a way of splitting our data. And then the n estimators just means we're going to make 100 of these trees. That is the kind of default metric that random forest classifier uses. We can increase or decrease that, but 100 is pretty sound. So right now we're fitting our model on our training data. So this is going to be teaching our model what decision trees it should create and how to split them. So we're going to be using our X train, Y train to fit our model. Remember, this is the 90% training sub data frame from our data set. And then finally, we're going to make predictions from our testing inputs, our testing X variables that our model hasn't seen yet, to make predictions of the outcomes. So now we're going to compare our predictions with the actual outcomes in our Y testing data set that our model hasn't seen yet. So right now I got 91.6%. That's I'm happy with that. That's pretty good. That's solid. So, and finally the confusion matrix. We went over that in the slide a little bit, but it's just a way to kind of learn a little bit more about your model. So let's bring this back up. So obviously my confusion matrix is a little bit different, but predicted a win and it actually won, predicted a loss, actual loss. So our model, we predicted a win when we actually lost, and then we predicted a loss when the team actually won. These are these 1-1s right here. And then we predicted 10 wins and the team actually won 10 times. Predicted a loss 12 times and the team actually lost 12 times. So it's a little bit more just to understand what's going on with your model. This is a way that I checked my model. So it basically, I ran my model on the training data that it already has seen before to make predictions, and then compared that to the training data it's already seen. Obviously, we should get 100 or very close to 100 because this data the model has already seen before. So this is all of our predictions in a nice little data frame. So this is the train test split, the random, just absolutely random inputs that it has decided. So let's look. So for example, let's look at 25 and 26. Predicted to win both of these. We can go up into our data frame. 25. So we won. We were a 6-point favorite. That's what this last column is. And we won and ended up winning by actually 6 points, the point differential column. Same thing with 26. We were actually predicted to lose by 4, and we ended up winning by 4. But our model predicted a win, and we did win. So that's interesting. You can kind of see all the predictions. And then, so this is, moving on. So these are all the predictions again. It's the same data frames, 25, 26, 29, 36. And these are the proportion of votes. Remember in our slide deck, we were talking about how each decision tree would vote a win or a loss. So there's the proportion of votes that voted to win or voted to lose. So for 25, 76% of the decision trees voted to win, while 24% voted to lose. So obviously more of them voted to win, so that's why we claimed as a win. We use the model.predict proba function, predicts probability function, and indexing by our X testing data index, and then we sorted it by using the same index. So finally, we just combined all of our data frames together. So right now, these are all of our predictions, 25, 26, 29. The win-loss, what our prediction was, what the actual outcome of the game was. This is where our data frame 3 came into place from the very beginning. And then we made this little separate column just to easily check, is this equal to this? If not, if yes, if not, no. So our model, this is interesting. So our model predicted that we were going to, with 98% of the votes predicted a win and 2% predicted a loss. And we ended up predicting a win, but LeBron James' team actually lost. So we're incorrect. So let's look at 54. That's a very big difference. 54. So LeBron James playing for Cleveland against Orlando. They were a 7-point favorite, and Orlando ended up beating them by 1 point. So that was a buzzer beater. It must have been in May of 2009. Interesting. So this is in the first round of the playoffs. That must have been when Orlando had Dwight Howard and like Hito Turkoglu when we made that little run. As you can tell, I'm a basketball fan. So yeah, this is kind of the most I think useful data frame from our model. It kind of tells us everything we need to know right here. So we're 91% correct, 91.6% correct. So which ones didn't we predict right? So is this one 54? This one right here, 174. So it's missing 2, 91%. All right, yeah, sweet. So there's a way to, the next thing is the way to kind of check our train test split. So results.size is just how many inputs are in this last data frame. This is our results data frame right here. So 120. So let's do the math. Our testing data set is 10% of 240. So 240 times 10% should be 24, right? 24 rows. And then we have 5 columns. So 24 times 5 shouldn't be 96. I changed that. Yeah, so 120. So it's just a way to double check that our model is operating the way that we expect it to. So we've built our model and we have investigated a little bit. We know a little bit about it. Let's make a prediction about a game that hasn't happened yet. So these are input variables, 1, 2, 3, 4, 5. And let's make a prediction about the game that will happen. When I was building this, there was LeBron James is playing in a game tonight, September 12th, against the Rockets. So it's the 10th game of the playoff run. Game 5 of the series. They're 6.5-point favorites, and the Lakers are home. And there's the second round of the playoffs. So 10, 5, 6.5, 1, 2. Let's put that into our model. Model.predict. And we predicted a win. Let's see what the probability is of our win. So we're using the same inputs here. We had a 99% chance of votes of winning, and a 1.01% of our trees voted to lose. If you're interested, LeBron James went on to win this game with the Lakers against the Houston Rockets. So our model was correct in predicting what actually happened. This game was interesting because it was played in the NBA COVID-19 playoff bubble. So our home and away doesn't really take into effect because of the bubble. There's not really a true home or away team. So I decided to just run another one. This is this same one. I think this is when LeBron James played against the Cavs in the finals against the Golden State Warriors. So game 17 in the playoff. It's game 3 in the finals. They were 24-point favorites, and they played home. They played in Cleveland. So there's a 93 proportion of votes to win, 7 proportion not to lose. And then LeBron James went on to obviously win this game with the Cavs. And finally, I think this is an interesting thing to look at. This just proportions out what factor or what input variables are more significant than the other one. So the most important one in our determination is the Vegas prediction, is the spread. So the plus minus. That's makes sense. The people in Vegas know what they're doing. The next closest one would be game per playoff run, and then game number, then finally series. Interesting just to kind of look how each input variable factors into the overall model and which ones are considered more important than the other ones. You can use this maybe if we got a factor that was very, very close to 0, we could take that out of our model. We determined it wasn't important. And then obviously to check, we want to make sure all of these add up to 1, because they're going to be a proportion of the model, can be more than 1. So I hope this was helpful to run through it. This code will be in the web courses module as well. Feel free to download it, look at it. Yeah, do whatever you want with it. All right, sweet. See you, everyone.